In this video, we discuss a special type of isomer referred to as a constitutional isomer. By the end of this video, you will be able to look at two structures of molecules and determine whether they are related as constitutional isomers. You will also begin to understand the relevance and importance of constitutional isomers and how these contribute toward the gigantic number of organic molecules that exist in the world. To begin our discussion of this, we will take a little bit of a review of earlier material. Specifically, we will look at types of isomers because this term has come up in earlier videos from this series. Specifically, in video 314, we talked about cis and trans isomers of alkenes. Cis and trans isomers are, more broadly, what we refer to as a type of stereoisomer, where stereoisomers are molecules that have the same molecular formula, which is going to be true of all isomers. In order for two molecules to be related as an isomer of any type, the compounds that you're looking at must have the same number and type of atoms, in other words, the same molecular formula, such as C6H12 for both of the molecules that you're comparing. In the case of stereoisomers, stereoisomers have a difference in the three-dimensional shape of the molecule. So they differ in their three-dimensional shape or their three-dimensional orientation. However, they have the same connections between atoms. So the same atoms are connected between the two in exactly the same order. So they just differ in how those atoms orient in space, like one of the atoms pointing forward in molecule A and that same atom pointing away from us in molecule B. So the same atoms have to be connected in the same order. In other words, the branches come off of the parent chain at the same position amongst the two compounds that we're comparing. It's just the branch would be oriented differently in three-dimensional space. And the example type of stereoisomer that we have looked at before, which is one subset of stereoisomers, were the cis and trans alkenes, where due to the fact that the alkene, carbon-carbon double bond, locks the atoms into three-dimensional space, what we found was that the Cis Trans Orientation locked, in this case, the two methyl groups trans to one another because one's going up relative to the carbon that it's bonded to and the other's going down, making this trans. In contrast, a molecule that's the same connections between atoms, meaning had an alkene group connected to two methyl groups, could alternatively have had those two methyl groups locked on the same face of the molecule in this upside down bowl type shape, whereas we follow the parent chain through, we see an upside down bowl, making these described as the cis stereoisomer because both of the methyl groups point in the same direction down relative to the carbon atom they're bonded to. But the connection between atoms is in the same order where we have a 4-carbon chain in both cases, and in both cases the alkene group is at carbon number 2 of that particular chain. Now, how do so-called constitutional isomers, the focus of this video, differ from the stereoisomers such as the cis-trans alkenes? In the case of constitutional isomers, what we will see is, by definition, two molecules that are related to one another as constitutional isomers will have different connections between atoms. So they have different atom connectivity. As an example of this, we could take a molecule that had 5 carbons in the parent chain, in the longest carbon chain as we think about our nomenclature. So 1, 2, 3, 4, 5. And we could put a methyl branch at carbon number 2 of one of the structures, and then a constitutional isomer we could draw by instead putting the branch at carbon number 3. So in the case of these two molecules, they have the same number and type of atoms, making them related as isomers, but they have a key difference in structure, which is in one case, the methyl branch comes off at carbon number 2, and in the other case, the methyl branch comes off at carbon number 3, meaning that the two have different connectivity between atoms. One way to recognize constitutional isomers is that despite having the same molecular formula, which is going to be true regardless of what type of isomer is present, constitutional isomers will always have a different Iupac name. And I'm not referring to the part of the Iupac name, such as Cis Trans, that dictates the stereochemistry. Instead, I'm referring to the parent name or the branch name. So they must have a different parent and or branch name when we look at the Iupac name. If two structures have exactly the same Iupac name, then the two structures would be the same molecule. They would not be constitutional isomers. So let's go ahead and attempt to apply this information, which, by the way, is one of the reasons why there are so many organic molecules in the world, numbering over 10 million, is because of the fact that organic molecules are capable of forming lots and lots of constitutional isomers. As an example of that, when we look just at alkanes, molecules with carbon-carbon single bonds, if we took a molecule that had the formula C10H22, we could draw a total of 75 different constitutional isomers for that molecule. Quite a lot. If we went up to 30 carbons and 62 hydrogen atoms in an alkane, that would have 4 billion isomers or more possible. Way too many for us to draw. And so the fact that carbons can connect in a variety of different ways to create a huge plethora of constitutional isomers accounts for the ginormous diversity of organic molecules that exist in the world. Let's apply this information that we've just looked at towards some sample problems that would illustrate how you could apply this information toward problems. In this example problem, we are asked to draw 3 alkanes that have a formula of C6H14 and are related as so-called constitutional isomers. There are far more than 3 total constitutional isomers, so you very well might come up with answers that differ from the ones that I will draw here. And that is fine, as long as the compounds that you have drawn, you can map out, have 6 carbons and 14 hydrogens, then you are good to go. The formula C6H14 will refer to acyclic alkanes, alkanes that don't have a ring, because if we think back to our earlier information, when we were defining molecular formulas that corresponded to alkanes previously, we determined that CnH2n plus 2, where n is the number of carbon atoms, will relate the number of carbons in an acyclic alkane to the number of hydrogens that exist in that alkane. So this formula here, we can say straight away will correspond to acyclic alkanes, because the acyclic alkane formula, alkanes that have no rings, no carbon atoms joined into rings, follows this particular map here. So thinking about ways that we can arrange 6 carbon atoms and 14 hydrogens into alkane, a few different possibilities include the following. We could take 6 carbons and we could just link them together into a straight chain. This straight chain having a total of 6 carbon atoms would automatically in the line angle formula have 14 hydrogens to fill the complete octet. That is why this formula works. This is the formula for filling the complete octet. And so we could go in and we could count how many hydrogens are present at each position, and I guarantee if we've drawn an alkane that the number of hydrogens will automatically work out. That's why this formula that we learned previously is so useful. Now we could go from there, and the way I strategize with making constitutional isomers is I start with something as simple as possible, like a straight chain of carbon atoms, and then from there build complexity. For example, rather than making a 6 carbon chain, we can make a 5 carbon chain. 1, 2, 3, 4, 5, and to get our total number of carbons up to 6, we could plug a branch on to the chain. And so that would give us, in this methyl branch here, our 6th carbon atom. And this would still have the formula, just as the first constitutional isomer we drew of C6H14. This would also have C6H14, because that formula where we relate the number of carbon atoms, Cn, to the number of hydrogens being 2n plus 2, applies toward any acyclic alkane, so it can have a bunch of branches if we want. The formula is still going to work out just fine. We could carry on from there and to make a 3rd constitutional isomer, because we're tasked with making 3 in total, we could move the branch from position number 2 of the chain to position number 3. And this would represent a different constitutional isomer, because the Iupac name now would change from being 2-methyl pentane to being 3-methyl pentane. If we change the name of the branch or the parent, then that is going to represent a constitutional isomer. And there are other possibilities here as well. The approach that I've taken for this is I've started as simple as possible, then I took 1 carbon off that simple chain and made it into a branch at a couple of different positions to go from there. Now, continuing on, I could take and make a 4-carbon chain, and then I can make a 2-carbon branch coming off of that, and we could check whether that perhaps is a constitutional isomer of the structures that we've drawn before. And to do that, what I'll do is systematically come up with the Iupac name. 1, 2, 3, 4, 5 is my longest carbon chain. Starting from the end closest to a branch, there's actually a tie here, so it doesn't matter what end you start numbering from. At position 3, there is a methyl group. And so this would have the formula C6H14, just like the other structures. But when we check our work here, which I always encourage you to do by thinking about what the Iupac name of this would be, or determining whether this is identical to one of the other structures that we've drawn, what we would see is that in determining the Iupac name for this molecule, we would find that the Iupac name is 3-methyl pentane. And that name is actually exactly the same as the name of the structure here, 3-methyl pentane, meaning that these two structures that we have just looked at are actually not constitutional isomers of one another, but it's 2 different ways of drawing the exact same molecule. So don't draw both of these structures down here. Draw one or the other when asked to draw out constitutional isomers, because the 2 structures here, since they have exactly the same Iupac name, are the same structure. They are not constitutional isomers. And so therefore, I am going to draw a line through this one to indicate that we do not want that to count as one of the constitutional isomers. So we've drawn 3 constitutional isomers here in our outline and in our answer for this problem. We eliminated that 4th structure that we drew because it turned out that it was identical to the 3rd structure. There's 3 constitutional isomers there. There are others certainly that we could draw, and to give you an example of that, I could take and make, say, a 3-carbon chain here, and then to get carbon 4, 5, and 6, we could do a 2-carbon chain here and a 2-carbon chain here. And if we determine the Iupac name for that molecule, 1, 2, 3, 4, 5, I'm trial and erroring a bit here, then there's 2 methyl branches coming off here and here. Oops, that would make a total of 7 carbons, so that's not going to work as a constitutional isomer because constitutional isomers have to have the same formula. And since this one had C7H16, that's not going to work because it's not C6H14. So what else could we do here? Well, playing around with drawing a total of 6 carbons rather than 7, which was the mistake in the last one. We could go 1, 2, 3, 4 carbons in the parent chain, and then 2 methyl branches coming off of that. Would be like so, and like so as the 2 methyl branches. That would give a formula of C6H14, and the name of that molecule would have the parent name butane, and as 2 methyl groups at carbon number 2, so it'd be 2, 2, dimethylbutane. And hence that structure with a different Iupac name but the same formula C6H14 as these other structures would represent a fourth constitutional isomer of C6H14. So there's a variety of different approaches to take for drawing different molecules that are related as constitutional isomers. You should definitely be able to do that. The way I like to do that is to start with simple, with just a straight chain, if that's possible, based on the molecular formula, and then build complexity by removing atoms from the chain and building those onto branches. And so we started with just a chain, then we did a couple of structures that had branches with the branches at different positions, and then we switched from having one methyl branch to having two different methyl branches on the structure. And there are other constitutional isomers that we could draw here as well to build complexity. And if I were asking this type of question on a graded assessment, I would ask you to provide a specific number of constitutional isomers. Like here, we specified to draw 3, because there are a large number of different constitutional isomers that exist for these molecules. And so generally, you won't be able to draw a comprehensive set of those for molecules that have much complexity at all. Here's another type of example problem that could reflect how you would be assessed on the type of information that we've presented in this video. Which of the following terms best describes the relationship between M for meta, ethylphenol, and P for para-ethylphenol? In order to answer this question correctly, you need to understand the relationship between the name and the structure of these molecules. So M, ethylphenol, is an aromatic molecule with a 6-membered ring with alternating single bond and double bond pattern, which we abbreviate with this circle inside a hexagon. And phenol, the parent name, refers to a structure that has a hydroxy group on an aromatic ring. So M-ethylphenol will refer to the branches at the meta position. So this is position 1, 2, 3. And that's our ethyl position here. So that's meta-ethylphenol. On the other hand, P for para-ethylphenol is an aromatic ring that has the hydroxy group on it, indicating that it's phenol. And then para refers to when the two groups are directly across from one another. So in other words, if the OH group is here, directly across from it makes the para form of this molecule, so p-ethylphenol here. Now, these two structures have the exact same molecular formula, but they have a structural difference in that one of them has a branch at position 1 and position 3 of the ring. The other has branches coming off at position 1 and position 4. That is going to make these two structures related as so-called constitutional isomers, because they have the same number and type of atom in both cases, in other words, the same molecular formula, but they differ in the location of the branches or the identity of the branches. So that would make these constitutional isomers. Let's do another similar example now. In this example problem, we are asked which of the following terms describes the relationship between the following two molecules that we see here and here. They could be the same constitutional isomer, cis trans isomers, or none of these. So let's take a look at, as the first thing, confirming that they are related in some way. They need the same number and type of atom to be either constitutional isomers or cis trans isomers, or the same molecule. If they have a different molecular formula, they're none of these. So taking a look at both of them, in both cases we see that the molecular formula is represented as C6, because there's a total of 1, 2, 3, 4, 5 carbons in this chain, and then a methyl branch would be C6. And since they have one alkene group, that means that they follow the formula of CnH2n. So I've calculated, based on there being 6 carbon atoms, that there must be 12 hydrogens. The same is true of the molecule here. If we count up the number of carbons, we will see that it is 6, and that there are 12 hydrogen atoms. And so, taking a look at these and comparing them to determine what is the relationship? Where the relationship is not going to be none of these. It would be none of these if these had different molecular formulas, like one was C7 and one was C6, for example. So now we need to determine what of these terms, A, B, or C, is going to describe how the two structures are related. Let's dive in and come up with the Iupac name for each of these molecules to determine whether they might be related as constitutional isomers. In determining the Iupac name, we always find the longest carbon chain, and we number that longest carbon chain starting from the end closer to the alkene group. Numbering from the end closer to the alkene group puts us with the alkene group here at carbon number 2 and a methyl branch at carbon number 3. So we would name this molecule in its entirety with the parent name pentene, ENE indicating it's an alkene. The alkene group starts at carbon 2, so it'd be 2-pentene. That's going to account for everything that we've highlighted in yellow. And then additionally, we have a methyl branch coming off at position 3. So we would call this 3-methyl-2-pentene as the Iupac name for this molecule, without yet designating the stereochemistry, without yet designating whether it's cis or trans. Now, for the other structure, similarly, finding the longest carbon chain for this other structure takes us through the molecule like so. We number that from the end closest to where a branch comes off, so it'd be 1, 2, 3, 4, and 5, finding that longest carbon chain. That's going to give us, just like in the structure on the left, the parent name of 2-pentene. And just like the structure on the left, the methyl branch comes off at position number 3. So we would refer to this as 3-methyl-2-pentene as the name for this molecule. And then carrying on from there, we look at the cis trans orientation of the molecules. And in the structure on the left, relative to the carbon on the left at position 2, we go down to find the longest carbon chain. Relative to the carbon number 3, the other carbon of the alkene, we go down as well. So we would describe this structure as being cis. Likewise, the structure on the right, when we look at carbon number 2 and we follow the longest carbon chain, we have to go up to find the next carbon of the chain. Relative to carbon 3, we have to go up as well. So we would describe this as being cis as well. Hence, these two structures have exactly the same Iupac name. So they are not constitutional isomers. We can rule that out because they were both 3-methyl-2-pentene. In both cases, we describe the structures as cis. So in other words, the Iupac name is the same, including the cis-trans assignment. And then that leaves us just with the two structures being the same molecule. And indeed, they are the same molecule, it's just two different ways of drawing exactly the same structure, where on paper, you can show the molecule in a variety of different ways by just rotating it around on the page. Since they have exactly the same stereochemistry designation of cis in both cases and the same branches and parent name in both cases, that means those two structures are exactly the same molecule, just drawn out differently. So in order to assign and assess that two molecules are the same, you either need to imagine in your mind rotating those around and being able to superpose them completely. That would mean they are the same. Or if you systematically determine the name for each of them, you find the name is the same, including the cis-trans designation, that's going to indicate that they are the same molecule as well. Let's do one more example of applying these concepts, where we're specifying the relationship between the two molecules that are shown below. We'll take the same approach as before, which is the first thing we will do is we will make sure that they have the same molecular formula. In order to do that, let's count our atoms. So in the case of the structure on the left, we have 1, 2, 3, 4, 5 carbon atoms. So we would call this C5. Since it's an acyclic alkane, we can apply the formula CnH2 2n plus 2 to reflect the number of carbon atoms relative to the number of hydrogens, so it would be C5H12 there. Then, carrying on, we can come to the other side, so this one, mapping out the number of carbon atoms. What we find in this one is that this actually has the molecular formula with 6 carbon atoms, so C6 in total. That would make the number of hydrogens equal to 14 using that CnH2n plus 2 equation. And this is going to tell us straight away that since these have different numbers of any type of atom, in this case different numbers of carbon atoms, that these have to be totally different molecules, that they cannot be related as isomers of any sort. And so with these being declared as not isomers of any sort, and definitely not the same molecule, that rules out all of the options except for none of these. These are just different molecules entirely. So based on the information that we have looked at in this video, you should now be comfortable with recognizing constitutional isomers and distinguishing between two structures if you see two compounds, to relate them as constitutional isomers, as cis trans isomers, as the exact same molecule, or as none of these. You should also be able to be given the molecular formula of a molecule and draw out some possible constitutional isomers by moving branches around or doing other things to make the number and type of atoms remain the same, but the Iupac name of the molecules change.